So on this one, it's an unknown experiment. So we're going to start off with either a carboxylic acid or an amine. We don't, and we're also going to have something, a neutral compound. It could be, well, actually, could be benzoin, which I had drawn up there, or some other molecules. Could be benzoin or fluorine. Or benzyl, which we worked with last time. So we don't know which of these it is, but we know that all three of these do not have a carboxylic acid or an amine. So all of them won't react with the HCl or the NaOH. So they're going to always stay neutral charge, no charge. And so then they can wind up in the organic layer the whole time. This is something we're going to have, and we're going to know we have it. We're going to treat this like an impurity. So we're going to try to get rid of that. There's going to be less of this. I think I'll tell you how much of everything, but I think there's like, I was aiming for about 0.5 grams of either an acid or an amine, and then like about, I think it was, maybe it was actually 0.5 grams of this. I think I was aiming for 0.4 grams of one of those two. And then this, I was aiming for 0.1 gram. Or no, it was half of all those, sorry. Yeah. Or was it? No, that was it. That was it. Well, I'll go tell you now. So anyways, once I have this mixture, I'm going to try to dissolve it in diethyl ether, because we did methylene chloride last time. I'm hoping they all dissolve in diethyl ether so you get to see what another organic solvent looks like in an extraction. And diethyl ether is, it's actually less dense than water, so now it'll be on the top layer instead of the bottom layer like methylene chloride was. And I'm going to start off by checking for a amine. So I'm going to add 1 molar HCl. If there's an amine in there and not the carboxylic acid, I either have one or the other, it'll get protonated, it'll go in the aqueous layer, right? And then the rest of the things will go in the organic layer. So this aqueous layer that has the amine now with a positive charge, it's soluble. If I add 6 molar NaOH, I have two things that can happen. I'll either get precipitate or no precipitate. No precipitate. If I get a precipitate, does that mean I have the amine or no amine?
That would mean you have the amine, right?
Yes, because that means if I get a precipitate, I had the amine in there and it precipitated out.
Yeah.
If I see no precipitate, then I'm like, oh, nice. I guess I don't have the amine. Everything, I must have the acid then. And that's okay. I must have the acid then. And that's okay. That would mean the acid's just over here in the organic layer because it wouldn't react with the HCl. So at that point, then I would say, oh, now I'm going to do a sodium hydroxide extraction to make the acid go into the aqueous layer and then look for a precipitate. So let's see what we get. My safety goggles. And we're going to do this extraction. It's a larger scale than the last one. Not a real large scale, but the last one was really small scale. And the last one we did, it was with the centrifuge tube. Remember how we had our centrifuge tube, and I had the aqueous and the organic layers, and I pipetted to separate them. Now we're going to go a little larger scale, so the centrifuge tube is not as convenient. Instead, we're going to use what's called a separatory funnel. It's got the opening at the top, and then it's kind of a teardrop shape. And it's got a stopcock at the bottom, like a, what do we call that? A diurette. And you can let water out by twisting the knob vertical. Right now, it's not letting anything out. If I twist it vertical, it's going to drip out. Actually, if this is the first time you've used this for this semester, it's a good idea to test it first. So I'll test it. It's just some water. So I'll add some water to the top of it. And so far it looks good. It's not leaking. And when I twist it, does it drain? It does, and I can stop by twisting it more. Just going into a beaker here. There we go, it's looking good, huh? And then I have a cap for the top. I like these plastic ones the best. There's also glass ones, but plastic ones are the best. So if you put this on top, you should like tip it over and see if it spills. Nope, it's not spilling. It's looking good. And we're going to actually be shaking these a lot to get the mix of two organic and the aqueous layers mixed up. So yeah, I'm shaking and everything looks good. So I'm happy with my separatory funnel, and I'll just go ahead and pour the rest of that water into here. Drain out. There's a little bit at the bottom there. There's not. Okay. And now, so my separatory funnel is good, and I have a ring stand over here that I've set up to hold it. And I have an iron ring. The iron ring was a little bit too big. This separatory funnel would slide through it. It wouldn't hold it. So I put some, I cut some hosing, some rubber hosing in half, like rubber hosing like this. I took a razor blade and I cut along the side of it so it can open up. And then I just kind of wrapped it around the metal ring. And then I took some copper wire and I just crimped it down to hold it all. So now it's like a softer thing to hold the glass, and it's also the diameter is smaller, so it'll hold it. It won't fall through. That. Okay, and something that happens all the time in extractions is you make the mistake of adding something while your stopcock is open. It happens all the time. So since it happens so much, and I don't want it to happen, I'll tell you what we're gonna do. We're gonna use this technique to save us. We're gonna put a security blanket under this. We're always gonna have a large beaker underneath our extraction setup. So we've got that large beaker there. So if I do happen to fill this up, like say I'm gonna go, oh yeah, let me get my organic layer. I'm gonna add this to my separatory funnel. Let me start pouring it in. And then I realize, oh no, it's spilling. I forgot to close it. It's in the beaker, it's no problem. If I don't have the beaker there, then the stuff just spills all over the counter. And that's happened a lot. And we don't want that to happen because it's a hassle. When that happens though, chemists don't give up usually. They're like, oh no, we gotta get this going. So what they do is a lot of times you'll take paper towel and you'll like soak up all the solution, and then put it in a beaker and add an organic solvent to extract it out of the paper towel and then put it back. But if your counter wasn't clean, now you have more impurities. But you still will do it if you spent, say, like a month trying to make a particular molecule. You don't want to just give up on the counter. I'm set up here with my separatory funnel. And actually, I'm going to get rid of this last bit of water. And I'm not too worried about the fact that my separatory funnel has a little water in it, because I'm going to be using aqueous solution. So it's fine to be a little wet right now. And I want to start off by telling you what I have here. This is what I weighed this out earlier. Actually, last time I was here, was that Tuesday? On Tuesday, I weighed out some solids to do our extractions of. So you can see there's different colors to that. You can tell that it's not all the same thing, you know. Okay, what I have in there is I have a neutral compound. And when I say neutral compound, I mean something that's going to remain neutral. It's not going to get a charge, not a negative charge, not a positive charge. It's going to, and I weighed out 0.4899 grams of that. I weighed it out on the scale last time. This neutral compound could be, as I said, like fluorine. I have to grab another pen. Fluorine, which has it's two benzene rings that are connected between a 5-membered ring like this. It could be fluorine. It could be benzyl. That's the same one we had last time. It might not be that one since we already did that one. Or benzo or benzoin, a racemic mixture. Actually, it's got a stereocenter. We bought the racemic mixture because it's less expensive. Okay, so it's one of those. We're going to figure out what this is because we're going to isolate it. We're going to separate it from the other two molecules. And then we're going to do NMR and IR. So we'll know which one it is. We can probably tell right away with IR, we should be able to tell without even taking an NMR. Can you, well, what would I look for, do you think, to tell which one was which?
There wouldn't be a carbonyl signal.
If I see a carbonyl signal, it's going to be either the benzyl, or the benzoin. Huh? They both would have.
Yeah.
It's going to be one of those. If I don't see a carbonyl, then what do I got?
The third one, the fluorine, or I forget exactly what it was called.
Yeah, I can't name it either.
Fluorine. It's weird.
Fluorine.
It felt like it had the fluorine atom on it, but it's not. But because it fluoresces. So yeah, it could be fluorine. So, but how would I tell? Say I see a carbonyl on 1700. How do I know if it's benzyl or benzoic?
You could look for the alcohol signal in the IR.
Around 3300, right? If we see that, then we're like, okay, I got benzoin, easy. Okay, and then we also have an amine, and I added for the, I mean, not an, I either have an acid or an amine. So the amine or acid, I weighed out 0.3800 grams. And I'm gonna give you this information in the Google Doc later as well. I just wanted to let you know what we got going here. And then so the acid could be benzoic acid, like that. Or I put R right here. If R equals H, it's benzoic acid. If R equals a methyl, then it's orthotoluic acid. So we either have benzoic acid or orthotoluic acid. We don't know yet, but we'll be able to figure that one out with, we can figure it out with IR as well, alone, but NMR, we'll take NMR as well. And then our amine is either gonna be benzocaine we had last time, the numbing agent, ethyl-4-aminobenzoate or benzocaine, or 1-naphthylamine. So we either have an amine, one of these two amines, or an acid, one of the two acids. We only have one of those four. And we're going to figure out, first, during the extractions, we'll figure out whether it's an acid or an amine. And then with spectroscopy, we'll be able to figure out if it's, say, it's an acid, which acid, or if it's an amine, which amine. And finally, I added dibromobenzene, BR2. And it's para-dibromobenzene. It looks like this. And I've added 0.1181 grams. So I have less of that, huh? I only have about 0.1 gram of this, where I have about 0.4 of the amine or acid and about 0.5 of the neutral. So I'm going to be treating this like an impurity. I'm going to do a crystallization to get rid of that at the end. Okay, so let's start off. Let's start going. I'm going to initially see if this will dissolve in diethyl ether. Hopefully it will. I put it in the beaker because if it doesn't dissolve in diethyl ether, I'll be able to evaporate it pretty quickly to try then another organic solvent like methylene chloride. But I'm hoping I'm right with the diethyl ether. So let's get the diethyl ether. It's over in the flammable cabinet. I'll go grab that now. So remember the flammable cabinet's over here, the yellow one. There it is. Diethyl ether. It's in the aluminum can because it's very flammable, and if it accidentally like falls off the counter or something, it's not going to break as easy as glass. Okay, and now let's start adding some diethyl ether. All you really need to do is just kind of pour some in and just roll around and look and see how it goes. So here, I'll set up a stand for this beaker. See what you guys think. I got my graduations on the side. I'm gonna aim for about like 20 milliliters or so. Okay, so far I probably added about, I don't know, 10 milliliters. And it's looking pretty good. Still some undissolved though. Let's go a little more. Might have to go a little higher than 25. Okay, let's swirl, let's see. Something's not liking the diethyl ether. I'm kind of bummed. I was hoping it would work in diethyl ether. I wanted to use that. Let me try a little more. Maybe I just need more volume. Oh shoot, I just swirled it up in my hand. Darn it, diethyl ether is not gonna work. Doesn't look good. Let me do a little more to make sure, but I don't want to have to go too high of a volume with this. I guessed wrong.
So now do you have to add a different solvent, or do you have to like evaporate away the diethyl ether first, or just gonna add
I'm gonna
more
go ahead
diethyl
and just
ether?
let that sit, and I'm gonna save that. If I need it, I can, if I need, so I'm gonna actually just prepare a new sample. But then I'll let this sit in case something goes wrong with the new sample. This can evaporate on its own, and I can still use it. It's not lost. Here, I'll wash my hands first. It swells on my hands. My hands don't feel numb. So first thing I'm going to do is zero out the beaker. Actually, before the dibromobenzene, I'm going to add this one here. I'm not letting you see the label, but it's a white solid. This one is the neutral compound. And I want to add about 0.5 grams, 0.5 grams. So should I add it while it's in the scale? No. I'm going to take it out of the scale. I'm looking for about a half a gram. Let's see what that is. 0.19. So I need a little more than double that. 0.3. 0.399. All right, 0.423. I'm going to go with that. I'll get my notebook and write it down right away before I forget. So 0.4213 grams. Got it. Next up, I have my acid. It's either an acid or an amine. It's a kind of off-white solid, a little bit yellow. And I want to tare this now. So I start back at 0. Then I'll add about the same. I'm going to add about the same amount, about 0.4. That's 0.14. 0.24. Okay, we'll go with that. I've got now of my either an acid or an amine. I have about, oh, look at that, 0.400. So not that, that's 0.4130 grams. Okay. Finally, I need to add my dibromobenzene, which unfortunately is in the stock room in the back, but I'll be back in 1 minute. And I just want a little bit of this dibromobenzene, like I was saying before, so that it's I'm treating it like an impurity that I'm going to get rid of. So tear it again and add about 0.1 grams. All right, 0.1222. Tap that, keep it fresh. 0.1222 grams. All right, back in action. Now the methylene chloride, or the diethyl ether didn't work so good. Methylene chloride. Go get the methylene chloride out of the flammable cabinet, and I'll return the diethyl ether. Too bad. Diethyl ether would have been nice to see it upper layer, lower layer, but that's okay. So methylene chloride, here we go. Diethyl ether, back in we go. Whenever I do these like experiment, usually I'll demonstrate some things in a normal setting, not the full experiment, but part of an experiment. I feel like I'm doing like a cooking show. I'm Rachel Ray or something. So first we add a little EVOO. Okay, so now we got the methylene chloride. Let's see if it works better. Yeah, I think it's looking better. Right about 25 milliliters. Let's add a little more. Wouldn't mind going to about 50. Yeah, I think this is going to work. I see a few little specks that are just taking their time, but I think that's what we want. So I guess it was good. We got to see what you do if you don't get the right choice. When I'd have you do this, when you do this experiment on your own in lab, if you were in lab, I would tell you to try methylene chloride or diethyl ether. And like most, like it's just you get lucky. If you got lucky the first time, you'd use that solvent. You didn't. So some students wind up using ether, some use methylene chloride. Okay, so I'm looking good. Got it all there. And then I'm going to add it to my separatory funnel, start going. So my separatory funnel here, I'll use the Shruxem funnel, and I'll open it up at the bottom. And should I pour it in while it's open at the bottom? No.
Get it all over your countertop.
Yeah. Close it. Right? There's a little bit of water. Okay, so yep. But I do have my security blanket there, just in case I make a mistake. But I'm not going to do that. I'm going to just carefully pour this in. If I want, I can lift it up slightly too, so air can come out as it fills. And now I probably still have some sample inside of this beaker. What should I do, you think, to try to transfer all of that? Oh yeah, I can already see it like precipitating back out. Does anybody have an idea of what we can do there? Just use some more methylene chloride. Watch it out. So I'll drop some methylene chloride. Shoot that in there. Actually, I'll go a little more than that. Swirl it around, pour it in as well. I'll do another one, try to get the side walls washed down good. Whoa, did you see that? How the methylene chloride was shooting out? That's what I warned you about before. I should have drawn some out, spit it, drawn some out, spit it out. Right now I'm evaporatively cooling the pipette so I don't get that elephant spray of organic solvent like I just did. I did that on purpose just to show you. It wasn't because it's one of those days. It was intentional.
An impromptu demonstration.
All right, so now I add it. And I'm happy. I got enough. Okay, so I've got my organic solution here. Let me start drawing out my extraction diagram. So at the start here, I might have, I could have either an acid, carboxylic acid, one of the two, benzoic acid or orthotoluic acid. That's one thing I can have. Or I could have an amine. I'll just write RNH2. It could be benzocaine, or 1-naphthalenamine. And I know that I have dibromobenzene. That's not a secret because I'm adding that as like an impurity to force us to do a crystallization. And then I have a neutral too. I'll just write neutral. I'll just write N for neutral. And then neutral is like a benzyl, fluorine, or benzoin. All right, and I have methylene chloride right now too. So I want to check and see if I have the amine first. What should I add to this to check for the amine?
HCl.
Yes. I'm going to add 1 molar HCl. 1 molar, not 6 molar, right?
Yeah.
What's 1 molar HCl mostly?
Water.
Mostly water.
Mostly water, huh? And then what else?
You'll get some hydronium ions, some chloride ions.
Yep. Good. So I know in this aqueous layer, I'm going to have mostly water, chloride, and hydronium. And maybe I'll have the protonated amine, right?
Yeah.
Okay, so let's do it. So volume-wise, I added about 50 milliliters of organic. You're always going to add excess. I'm going to go with about 25, which is still a large excess. But are we under really good reaction conditions here? No, we're not under really good reaction conditions because I'll show you once I mix it, once I add it. So I'm adding my 1 molar HCl. And these reaction conditions are not great because there's an aqueous and an organic layer, and they only react at the surface. So I always want to have an excess of the acid or base in extractions. But another thing that will help this reaction take place, instead of having to just let it sit here and wait for all of the reaction to take place just at that one interface, what can I do to speed things up?
Turn it over and shake it and
Shake
agitate it.
That's right. Okay, and when we shook the centrifuges before, what did we do? How did we do it? What did we do first? Did we just start shaking it like crazy at the start?
Turned it over once and then you vented it.
Yeah, we did. We were gentle at first. We vented a lot, and then we gave it a good shake. So I'm going to do the same thing here. So when you do this, you want to make sure your cap is good. And I like to hold it like this. I put my 2 fingers across the cap that way, and then I grab onto the rest of it. So I'm holding it nice and snug, and I'm pushing down on the cap. So I don't want the cap to come off. So I'm holding the cap good. And then I always point it away from me towards like whoever in the class is the most annoying. And then I vent it. Just kidding. I don't point it to anybody. I point it at the back of the wall of this sink area right here. So if it does vent out, it doesn't hit anybody. Don't point it at anybody. Especially don't point it at yourself. That's like the worst thing you can do. Okay, now I'm gonna go back. Go just real gentle. Forward again and then vent. Did you hear it? Oh, sorry, I wasn't showing. It's venting pretty good actually. Getting less. I think if I do it this way, it'll look better for you. Yeah, see, I'm pointing it away from me. It's still venting. Sometimes a little bit bubbles into there. I'll put that in a beaker. Okay. And now I think I can start to give it a little more of a shake. Now it's bubbling up in there again. More of a shake. Now I can start to be a little more aggressive. I'm allowing it to react much more if there is a reaction. So the 2 layers are getting more in contact. Okay, and then I shouldn't make this joke, but I could do Wei Che's joke. When I was in grad school, one of my lab mates, Wei Che, was a brilliant organic chemist from Taiwan. And he would say, yeah, you have to hold it really good and secure like a baby and then shake it. I was like, Wei Che, no, don't shake. He was joking. You don't shake babies, but you shake your separator. Give it a good shake. All right, so I think it's good. Another way I can vent too, I was venting from the bottom there when I take the cap off. And that's another thing. When you put your separatory funnel up to sit, you put it up here to let it separate out the 2 layers. When you put it up here to separate out, always take the cap off. Never leave it up here with the cap on. It seems like you'd want to leave the cap on, but what happens is that a lot of times when the layers are separating, it builds up pressure and the cap will go pop off. And if it's this plastic one, it's not such a big deal usually. But when it's the glass one, we've lost many of those where the student will leave it here and then after the pressure builds up, the glass thing falls and it breaks. So we don't want to do that. So you always want to take your cap off when it's resting. All right, and it's separating. And it separated out well, huh? See the 2 layers?
Yeah.
Yeah. And so which layer is on the bottom?
The aqueous layer this time. Or no, it would be the organic layer because you use methylene chloride.
Yeah. So I'm going to write on this this Erlenmeyer flask, organic layer. All right, first organic layer. I'll write my initials, date 3/18/21. Okay. And now I'm going to drain that organic layer. I got to move my beaker out of the way, but it's okay because I'm going to be purposely opening the stopcock now. So I'll put my, actually it's best to have it on the counter. Okay, there we go. Let me get you a better view. So I'll start opening the stopcock and I'll start to drain out that lower layer. And I'll let you watch as I go. So I start off. Can you see? Oh, you can't see it yet. Can you see the organic layer coming down? And when it gets close, I'll stop it. Maybe I think it's better view video-wise if I turn the stopcock away. There There we go. So now I can keep draining it. I try to get just I try to separate the layers perfectly, but it doesn't always work out, but you do your best, you know. And now I still got some organic on the bottom. Before I proceed, what I like to do is tap the side of this. Occasionally there'll be a little bit of organic layer stuck on the surface tension of the water, like little bugs walk across the lake water because of the surface tension. I have some organic up there, so I'm gonna tap it a little bit. And then I'm gonna drain some more, and I'm gonna try to get it separated well, but it won't be perfect, but it's okay. I'm actually gonna err on the side of adding just a little bit of water to the organic layer. Okay, so I've got them separated. So in this layer, the organic layer, I should have my neutral compounds, the dibromobenzene, and maybe benzoic acid or one of the acids if it wasn't an amine. Up here, I might have an amine, huh? Remember that? Oh wait, I feel like, yeah, I got some more organic layer to fall to the bottom. Can you see it?
Those
Little beads.
bubbles that were flowing the wrong way.
What?
Like they looked like little bubbles that were going down instead of up.
Yeah, that was a little bit, that was just the more dense methylene chloride beads. All right, so I got those two. So now what I want to do is I want to check for the amine in here. I mean, well, it's actually currently, if it's in there, it's ammonium, right? So I'll put that in a different Erlenmeyer. I'm going to label it first aqueous. It's really important that you label all these because we're going to have a bunch of these and it's easy to mix them up. First aqueous, 1 molar HCl. My initials. 21. Okay, there we go. So now I'll just drain out the complete lower aqueous layer. Or now it's not, it was upper, now it's lower. It's only layer actually. So got it. And then, so this solution should be, can you see it? This solution should be acidic, right? It's 1 molar HCl.
You test it with pH paper?
Yes, there you go. Let's check it with pH paper though. Let's make sure. So I'll get a little bitty piece of pH paper. I'm going to get a couple because I'll be checking it. I'll be changing the pH and I want to check it then too. And now to check the pH, should I just quickly dip in the top of it? Or should I really swirl it around? Get it, make sure it's wet, not swirl around there. All right, let's see. This should be acidic. Is it acidic? What do you think?
It looks red, so yeah.
Good. And how do I make it basic? I want to make it basic now. What should I add to it?
The 6 molar sodium hydroxide.
Right. Why don't I use the 1 molar NaOH? Why do I want to use the 6 molar NaOH? Because I'll only have to use a 1/6 of the volume. I won't have to add a lot. Because if I used 1 molar NaOH, I'd have to use that same volume. I'd have to use a lot. So I don't want to do that. Because if I add a lot of water, then there's going to be a little bit of water solubility for these things. All right, so far, does it look like it has amine in it? What do you think?
I think a precipitate is forming and then disappearing, but I can't quite tell because of the white
It
background.
does kind of look like a precipitate, huh?
Yeah.
But it's pretty mild. Let's check. I just added another squirt. I did like about 3 squirts. So I think I've added plenty to make it basic. Let me check the pH. Now, remember, I don't want to just do a quick dip. I want to really wet my spatula. Let's check. Oh, it's definitely basic. So what do you think? Does that look like we have precipitate, or is it maybe just a little bit cloudy? This one is a tricky one. I have a lot of students get caught up on this because it sort of looks like a fine precipitate, but I know it's actually not. I think I need to stop using the benzocaine. I like benzocaine, but it doesn't precipitate out that well. And so when you get something like this where it's not a precipitate, it sort of looks like last time's benzoate. Huh?
Yeah.
So yeah, this I'm gonna put this down as not a precipitate, and I'm gonna proceed as if it isn't, and then we're gonna see if we check for an acid and we. Here we go. Okay, so I'm gonna set this aside. I'm not gonna get rid of it. I'm gonna keep it for now. It's labeled. I know what it is, but I'm gonna now proceed as if I don't have the amine. So let's write down what just happened to. So I added 6 molar NaOH, and I added about 3 milliliters, and the pH paper was blue. This pH paper was pink, huh? Okay, so what should I have in solution at this point? If I say it looks like no precipitate to me, what's it mostly made up of here?
Mostly have water. You'll have some chloride and you'll have some hydroxide.
And one other thing, had the hydroxide come? What did it come as?
Sodium
Sodium.
ions.
Good. So let's assume that's the case. So what I'm saying then is that I don't think I have the amine. I think I have an acid. So then over here, I would have what's the main, what do I have mostly in this organic layer over here?
Methylene chloride.
Yeah.
Chloride, what else is in there?
You have your acid still.
The what?
Oh, your acid would still be in there?
Yeah,
right?
the acid, yeah, good. And
Your dibromobenzene.
yep, C6H4Br2 and
Trace water.
trace water. And then there's this neutral compound too, like could be fluorine, benzyl, benzoin.
Oh, you're unknown.
So I've got all those, and so let me go to a new page and rewrite that. So what do we want to do at this point then? I've got
Is this where you add 1 molar sodium hydroxide and then you'll add 6 molar hydrochloric acid to see if you have to check that you have the acid in the solution?
got it. Good job.
Cool.
So I feel like I have an acid in here, right? And I'm going to add about 20 milliliters of that. I feel like I have the acid. If I do have the acid in the organic layer, will it react with 1 molar sodium hydroxide?
Yes.
1 molar. It will, huh? So I'll get the carboxylate. That's one of our big 4 reactions. And why is the carboxylate over here in the aqueous layer now?
Because it's charged.
Yes. What else do I have in this aqueous layer?
You have the water, you're gonna have hydroxide, you'll have sodium.
There you go. So let's try it. I'll fill in the rest after you got it. So I've got my first organic layer. I saved it. I'm going to add it to my separatory funnel. Before I add it, is the stop clock closed?
Looks like it.
It's closed. That's good. So let me add it to the top here. Wait. First organic layer. Okay. And if I want, I can add a bit of methylene chloride to this, rinse it out a little more. Okay. And next up, we said 1 molar sodium hydroxide. There we go. I got some 1 molar sodium hydroxide. How much do I want to add? I'm going to add about 20 milliliters, I said. I'll use this original beaker. That's 50, that's 25. I'm going to go a little below that lowest line. There we go. So I've got my 1 molar sodium hydroxide in here. Get my cap. And I will first carefully tilt it, point it towards someone I love. No, don't love. No, don't point towards anybody. And vent. Another slow twist and vent. Can you guys hear it venting a little?
A little bit, yeah.
Good. Okay, now I can give it a little more of a shake. It's got a nice vent to it. Shake, shake, shake. Shake, shake, shake. Shake your booty. Ow. All right, yeah, let's get one more. I'll get one more shake.
So the gas that's venting, like, what is that? Because the last time that you were doing this, you were venting and I could hear it then as well. But we're saying that there wasn't the amine in there. So there wasn't that reaction going on. But there is, is there some gas producing reaction, I assume?
Yeah, yeah. When you if you just take methylene chloride and water, pure methylene chloride, and you shake them up in a separatory funnel like this, when the two solutions mix, it's actually exothermic when they come back apart. So it creates a little bit of heat, and that heat takes the methylene chloride, which is got low boiling point, high vapor pressure, creates a little bit of pressure. So you don't even need a reaction to take place.
Gotcha. Okay. Would the same thing happen with the diethyl ether?
Yes, yeah, diethyl ether even more so. It's more volatile. Okay, so I've got 2 layers, right? Can you see it? That top thin layer at the top, that's my aqueous or organic up top. I started with about 50 milliliters of methylene chloride, and I just added about 20 milliliters of 1 molar NaOH. So
aqueous is on top.
Yeah. All right, then my Erlenmeyer had said first organic. It's empty now because I poured it back in. I'm going to call it second now. And I'm going to drain off this lower organic layer. Okay, here we go. Oh, and I've taken the cap off. Like I said, we always have to have the cap. Let me show you something actually. Well, yeah, so this is a real common mistake. Students will keep the cap on and they'll try to drain the sample, and watch what happens when I try to drain it. It just stops. Huh? It's because it builds up a vacuum up top. So I always have students say, oh, my separatory funnel is broken. It's like, no, just take the cap off. And now it'll drain until you tell it to stop. So we're draining. And now you're going to see the 2 layers coming down. And as it gets close, about here maybe, I like to stop. And then, as I said before, you give it a tap. And you get some of these, might be hard for you to see because that upper aqueous layer is cloudy, but I see little beads of organic layer dropping down. And I keep draining, go slow. Oop, almost there. And this time, I'm actually going to err on the side of putting a little aqueous in here, because if I have organic in this aqueous layer, then there's a problem with when I try to make a precipitate, instead of seeing that precipitate, it dissolves in a little bit of organic that's there. So I'm going to drain a little more, make sure I get all that out. Okay, I feel good about that now. So then I'm going to drain this, which is my upper layer. This is my second aqueous, the 1 molar sodium hydroxide, and my initials, date. And I just drain out the whole aqueous layer. And it looks a little bit like chunky in there. I'm gonna give it a little DI rinse. This is gonna be two things I'm gonna do. I'm gonna rinse a little deionized water down through the top. And what that's gonna do is it's going to, wash it out. And also it's gonna confirm that this is the aqueous layer. Because if it isn't the aqueous layer, I should see like a separate layer forming down below. Do this, I'm gonna get it to go. There we go. Now I'm gonna drain that out. Okay, looking pretty good to me. And I'm gonna right away put my safety beaker back underneath. So if I make a mistake later, I know I got something under it. All right, so here's my aqueous layer. Should it be acidic or basic?
Should be basic, right?
Yes, 1 molar sodium hydroxide should be basic. Why don't we check just to make sure before we switch it? I'll get just the little bits of pH paper. Get the spatula. And I'll stick it in there, swirl the spatula around good, make sure it's nice and coated, and check it. Is it basic?
Yep.
Definitely basic. Okay, looking good. And now I want to make it acidic, right? Because I believe there's a carboxylate in here that I want to protonate with acid. So which acid do you want me to use? Should I use the 1 molar sodium hydroxide or the 6 molar sodium hydroxide?
6 molar.
1 molar HCl hydrochloric acid or 6 molar hydrochloric acid? Let's see if I'm right about this. If you do have a carboxylate in here, we should see right away like a precipitate form and then dissolve. Let's go. Ooh, nice, huh? Yeah, that's definitely more significant of a precipitate, right? Oh yeah, look at that. There we go.
Yeah.
And then when I swirl it around, it dissolves. Who can explain that?
That's the local high concentration of HCl deprotonating or not deprotonating, protonating the
Carboxylate.
acid. Yeah, the carboxylate into the carboxylic acid, which is precipitating out. But then once you swirl it around, then it mixes in with the rest of the sodium hydroxide and deprotonates it again, turning it back into the carboxylate.
Yeah, this is basically like a titration.
It back.
Yeah, very good, Morgan. This is like a titration. That's basically we have a precipitation indicator. You know, we did titrations and you had color indicators. This is a precipitation indicator. Kind of cool, huh? Now you see starting to get to the point where we've quenched all the sodium hydroxide. Not quite. So do you think the solution is acidic or basic right now?
If the precipitate is not sticking around, then it should still be basic.
Yeah,
but once it starts sticking around, then it's neutral or acidic.
Let's check really quick since we're here. Why not? Okay, let's go. Swirl my thing around. Let's see. Is it still basic? Still basic. Good job. Let's go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Whoa, now it's starting to go. Oh, it's staying. We've either reached the equivalence point or we've gone past it. Or maybe we're right below it. We're close, right? Do you think it's acidic or basic right now?
Acidic.
Should we just assume it's acidic or should we test it?
Test.
Always test it. Because sometimes you're not. You're like super close but not. And then the problem is you won't get a good yield. So let me check it. Oh, it's still not quite. Do you see that? It's not pink, huh?
Oh.
Not quite there. Good thing we checked. Let's do another good squirt. Give it a swirl. Looks like it got a little whiter, a little more precipitate formed. It's not always the best to use the same piece of filter paper, but I mean pH paper. But it looked like it did get pink, but I'll get a fresh one to confirm. Yes, it's acidic. Okay, we've added enough. I added probably about 3 milliliters, I think. And if I had used 1 molar HCl, I would have had to add 6 times as much. I would have had to add 24 milliliters. So it would have been a lot more water in there. And this acid is a little bit water soluble. So if I add a lot of water, I'm gonna, when I go try to recover it, it's not gonna be as high of a yield. So that's why I use the 6 molar. All right, that's nice, huh? Got our first layer precipitated out. Let's now write down what we did there. Make sure we don't lose track of what's going on. So we went ahead and added about 3 milliliters, 6 molar HCl, and it was had pH paper that was pink. Okay, and we saw a precipitate. Yay! What was the precipitate? Carboxylic acid. What else is in this aqueous layer?
Water and chloride and sodium and hydronium.
Yes, because now it's acidic, so we'll say there is hydroxide, but the hydroxide concentration is like so low. It's like 10 to the minus 14 or something. 10 to the minus 13 or something, really low. So 1 times 10 to the minus 13 molar. So then we got that there. That's great. So what happened on this side? What's on our organic layer, our second organic layer after this acidic, or there was a basic wash of it, and acidic? What's left in this organic layer? What's mostly in this organic?
Your CH2Cl2.
Yep, methylene chloride. And what else?
You'll have your dibromo
Dibromo.
benzene. Yeah. And you'll still have some trace H2O. And your mystery compound.
The neutral mystery compound. Yes.
Yeah.
There we go. And maybe some more acetic acid, huh? Maybe it didn't all come out in that first extraction. There might be some of that still in there, huh?
Yeah.
So should we check for that now?
Sure.
Yeah. How should we do it?
Following the same process as the last step, right?
Yeah. So this is my organic layer, second organic layer. Add it back. Oh, is the stopcock closed? It is closed. Add that back in. Oh, okay. And then after I've added that in, oh, I'm making a mess. This is the problem with Sharpie in my organic solvents. We'll wash it away. That's okay. But it's so convenient to write on it quickly. Here, I'll show you. This is the proper way. I should use this little white label. So this is going to be my third organic layer. So the thing that's nice about that pencil, when it's written on here, it won't come off if I run methylene chloride over it. All right, so here we go. We're going to go 1 molar NaOH now again, right? Let's do about 20 milliliters again. 1 molar NaOH. And our aqueous layer then should have perhaps the carboxylate. We'll see. Water, sodium hydroxide. And then we're going to treat that with 6 molar HCl till it's acidic and look for precipitate. Okay, let's try it out. And then we'll have our organic layer over here. I'll fill that in shortly. So molar NaOH. About 20 milliliters. There we go. Got the 2 layers. Oh, hold it. Shove this way. Twist it back. Point it at someone you love. No, no one. Little shake. Good. Shake it like a Polaroid picture. There we go. Good. Do you think we're going to get more precipitate out of this? We shall see. I've got it closed up. Put it back in my iron ring. And do I want to leave the cap on?
No.
Pull that off right away. Let the layers separate out. They're separating out pretty good. So I'm going to give it a little tap to help speed it up. Okay, and now this is going to be my second. That was the second aqueous, last one. That was second aqueous, first sodium hydroxide. Oh wait, I should label this a little more. Huh? So I got second aqueous, first sodium hydroxide. I should say plus 6 molar HCl. Okay. Now I'm going to say third aqueous. And 1 molar NaOH. And this will be my initials, MFS 31821. Okay. Now I just need to drain it. There we go. And that lower organic layer out. Go, go, go. Oh, yeah, now you see the aqueous layer on top coming into picture, huh? And then about an inch left of the organic. I'll stop and I'll give it some taps. Do a little more. Stop and give some taps. Some of those beads of organic to fall through. Boom. You're trying to be super precise about this, you can go like, wait 5 minutes and really let it separate. But for our purposes, this is fine. Okay, so that's my, oh, you know what? I labeled this wrong, huh? That's not my third aqueous layer. This is my organic layer. Because the lower methylene chloride there. Whew, good thing I caught that, right? Easy to get mixed up on these. So this is going to be my third aqueous layer. And it's 1 molar sodium hydroxide, MFS 31821. Okay. Drain that in. I'll rinse it out with a little DI water. Okay, so what should this be, acidic or basic?
Should be basic.
Yeah. And you notice I keep checking the pH with the pH paper even when it's obvious. It's a good idea to do obvious stuff like this because you're just, it's nice to find a mistake right away. You know? So I'm gonna still check this even though I'm like 99% sure it's all good. Should be basic. It's basic. Good. Okay. And now what do I do to it to look for precipitate?
6 molar HCl.
Got it, 6 molar HCl. So we should see precipitate like forming right away and then like dissolving. Can you guys see the flask well? Yeah, you can see it well. Ooh, I'm not really seeing precipitate. Last time I think I did about 3 squirts of 6 molar HCl. So I'll do 3, swirl, and check. Not seeing anything, but I gotta make sure I did make it acidic before I can say there's no precipitate. Oh, I made it acidic. Okay, great. That's good news, right? A lot of times when you don't get a precipitate, it seems like nothing happened, so it's not good news, but this is definitely good news. So let's look at our extraction diagram and figure out why this is. Make sure we understand what's going on. So that's my third aqueous. Oh yeah, and then this is also, this sodium hydroxide was made acidic with 6 molar HCl. I keep real good track of what's going on. No, not only will I not get confused, but after the end of the experiment, when I want to clean up, I'll be able to clean up properly. So I'll know, oh, that's an acidic solution. I should handle it as an acidic solution. Okay, so no precipitate. What does that mean? What does that tell us?
Means you got all of, or at least the vast majority of the carboxylic acid out in the last reaction.
Yeah, all the acid is here. So that means back here, no, I didn't have that. So I didn't have this. So what is in here mostly?
Water, hydronium, chloride, and sodium.
Getting it. Yeah, so I can dispose of that, quench it with some sodium bicarb, put it in the waste container. Over here, now I've already separated out one of my 3 molecules. I've gotten the carboxylic acid away from the neutral compound and the dibromobenzene. We're a third of the way done with this. So what do I need to do next? I've got, what kind of solvent in this organic layer?
Methylene chloride.
And what else is in here?
Got your neutral molecule, your dibromobenzene. What's the other one? Got your trace water.
Yep, that's it.
Okay.
So the neutral molecule, it could be like, maybe it's let's get, fluorine is one possibility. So it might be fluorine. So let's say I have fluorine, I have dibromobenzene. Dibromobenzene looks like. Okay, can I separate these two using acid-base chemistry by adding like HCl or NaOH?
I don't think so, because it's likely you would have done that already. Like it would have happened already.
Yeah, because for the acid-base step, we need either a carboxylic acid or a carboxylate or an amine or an ammonium. But this one has no carboxylic acid, no carboxylate, no amine, no ammonium. No carboxylic acid, no carboxylate, no amine, no ammonium. I cannot separate these with acid-base chemistry. So how am I going to get them separated?
Crystallization?
Yes, because I have more of the neutral compound. It might be fluorine. I have about 4 times as much. So I'm going to treat this like it's an impurity, an impure solid. So, but if I want to have them as an impure solid, what do I need to get rid of?
You need to get rid of the water.
I got to get rid of the trace water, and what else?
And then you've got to evaporate the methylene chloride.
Yeah. Okay, so let's do it. I got my organic layer here. I'm gonna put it back in the separatory funnel, and you can see it does have water in it. Huh? Can you see the little, is it possible, little beads of water in there? Can you see it? On the bottom. It's not the beads of water on the bottom of the flask. It's not because water is more dense, it's just attracted to the polar glass. All right, so let's add that into our separatory funnel. Is it closed? It's closed. We're good. And then what should I do to, I'm using the separatory funnel to start my drying of the organic layer. So what am I going to do to dry the organic layer first? What technique am I going to use? I refer to it as like a pre-dry. What's this bottle? Does anybody remember?
Yeah.
Brine Wash. Remember, the Brine Wash is good for, I call it like a pre-dry. It's good at getting the bulk of the water out. Not all of the water, but it could get a lot out at once. So it's nice to do a brine wash first to get like, 99% of the water out. And then we'll use sodium sulfate to get that last 1%. So with the brine, I usually add maybe about the same volume you already have or half as much. It's approximate. I'm going to say, actually, I'll measure it out. I'll be good. Usually I would just pour it in with experience. You kind of get the feel for this stuff. But let's go about 20 milliliters, maybe 25 milliliters. That sounds good. Pour this in. Okay, cap it nice. Hold on to the cap and then pull the cap down as I tilt it upside down. Vents away from me. Give it a little shake. Vents. This one's not venting too strong. It's okay. There we go. Vent. So the brine is very salty, so it's drawing water into it. It wants to dilute the salt ions in the water. It's drawing water out of the organic layer, making the organic layer drier. Similar to osmosis, but instead of a semi-permeable membrane, you have two heterogeneous layers. And you'll notice, I don't know if you noticed, you might not have seen it. The brine separates out quicker than the other aqueous layers, because it's I think of brine as like more polar than water and more polar than the HCl and NaOH, so it separates out really well. And it looks like to me, I don't know if you can tell, that the organic layer got clearer. Does it seem a little more clear than before? I'll try to like screenshot it for the report.
It might look a little bit more clear. It's kind of hard to tell on the video, at least for me.
It's kind of hard. Okay, and so now I'm going to put this organic layer into, it's Erlenmeyer again. Organic layer is on the bottom, of course. It's methylene chloride. And now, there's something interesting. See at the top, it's got this like hourglass shape. Can you guys see that? This happens often. You'll get, for some reason, some sort of like polymerization will take place. And you'll see a lot of times that kind of shape. And you can see it a lot of times between the two layers. You'll see this thin polymer. I don't know what.
I can see it.
Yeah. Interesting, huh? Or you say you can or can't see it, John?
I can't. It's like a thin hourglass.
Yeah, it's interesting, huh? All right, so I'm gonna stop a little early, start tapping. A little more. So now the top layer is my brine. I don't really want a lot of brine in my organic layer, but I don't want to lose any organic layer either. So I'll go get it really close. Boom, stop right there. I could, if I want, add some fresh methylene chloride to this, do another shake and make sure I got it all out, but I'm happy with what I got. And maybe I'll just go a tad more. Pretty good. There we go. Okay, so now I've got my pre-dried organic layer. My aqueous layer is left up above. If I wanted to check, I haven't really been checking as much as I usually do when I teach this, but I can shoot a little water into this and then check to see that it doesn't make 2 layers. It did not make 2 layers. That's definitely the aqueous layer. So I'm good with that being the organic layer. And I'm gonna add some sodium sulfate. I have my anhydrous sodium sulfate here. And I think we could see, definitely see some, I didn't get all the water out. There's some beads of water in there. I don't know if it's coming on, showing up on your video. Do you see little beads of water floating in there?
Yeah, sticking to the sides of the glass.
Yeah, you can see it on the side of the glass too. Yeah, good point. So you'll see that go away. Let's do it. So I just start adding sodium sulfate, and and as I add it, it should clump at first, and then it'll stop clumping. It'll be more granule. So it's clumping when it's hydrating. Right now, it's basically one big clump. Sometimes if you have a lot of water, it won't even clump at first. It'll like make a gel kind of thing. You see these little gel balls, and you keep adding, and then it starts clumping, and then finally it's not clumping, it's little grains. And then you're gonna notice it's gonna clear up, hopefully you see it. So it's looking pretty good. Add a little more. Yeah, it's getting there. I think. Go a little bit more. I think that's going to be enough. Yeah, I do see a few little grains on the bottom that are not clumping. I wonder. You know what? I'm adding more. I'm wrong. I think more. Yeah, I think I'm getting. I still see a little bit of water sticking on the inside. Try to get one more scoop. And then after I do this, if I want to be very good about this and do it properly, like not the most proper, I could cork this and let it sit for like 10, 15 minutes. Sometimes you'll actually swirl some out. Sometimes you'll let it sit till the next lab period. Like this would be a good pausing point if you're like running out of lab time. But I'm going to go ahead and decant it. And I'm going to decant it into a big beaker that I want to allow it to evaporate in. I'm going to use this beaker actually. And I'm going to put this under here. I'm going to wash this out really quick. And water takes a while to dry off your glassware. If you want to dry it faster, you can rinse the water out with an organic solvent that will dry after the water. So that's what I'm going to do. I'm going to get just most of the water off first. And then I'll bring it over to the fume hood. Actually, I'll do it in front of you here. I'll grab a little acetone. So I've got my bottle of acetone. And I'll squirt some in there to kind of grab onto the last residual water that's in here. And I'll put this in here. And now the acetone that's in here, it is very, got a much lower boiling point than water. So it'll evaporate quicker. And now I'll blow that acetone out quickly with some nitrogen gas. I'll show you over here. So once again, here's our nitrogen tank. Two gauges. One, the gauge closest to the tank tells you how much pressure of nitrogen is left in the tank. The gauge here is telling you how much you're letting out. Currently, it's closed at the top, so it can't read from either gauge. Before I open it, I want to check that this is open. This should be loose and open. It's open. I mean, not open, it's closed. Sorry, this is closed. So when I do open the top, I'll see the pressure of the inside of the tank, but it's closed. It's not letting any out. So now I have inside of here about 8,000 kilopascals of pressure of nitrogen. And now I'm not letting anything out. When I twist this in, I screw it in, I'll eventually feel it. That's the nitrogen gas coming. And so I could use that to like rich man's way to dry your glassware really fast. You wouldn't normally do this. It's wasteful, but do this quickly. And actually, as far as wasting goes, we've wasted almost nothing in lab this year since we haven't had all of you in here doing stuff. And now, after I've done that, then I'll make sure this is off. So I read 0, and then I close the top always, just in case this wants to leak. It's closed here as well. Okay. Then I'm going to go over and get the mass of this. So this is a big beaker. I don't think it's appropriate to weigh it in here. Yeah, it's going to hit the sides of the scale. I could lift that out, but I think this is still not really made for such a heavy object. So I'm going to weigh it on this top loading balance. This one's made for heavier things. So I'm going to initial this MS 381. And this is my unknown extraction. Organic layer. Okay, so this is reading 0 currently. I'll put that on there and see what it says. Well, I haven't been writing down. So evaporation beaker, 256.94 grams. And remember, we decant by just carefully pouring off the liquid in, but not the sulfate, the hydrated sodium sulfate. All I want coming in here is my organic layer. It's looking pretty good. Oops, I think I got a little bit of a Sharpie again. I shouldn't be using Sharpie. It's convenient to write with the Sharpie, but it's not the best choice for organic solvents. Okay, so I've got my sodium sulfate hydrate with the water. I'm going to rinse it out with a little more methylene chloride. Let's roll that around. Can't. Do it again. Do a couple rinses of it. Why am I using a beaker for this evaporation?
The extra surface area.
Yeah, exactly. All right, yeah, there we go. Looks pretty good. And this sodium sulfate hydrate, it has some methylene chloride on it. So I don't want to wash this down the drain right now because of the methylene chloride. So what I'll do is I'll just let this sit out, keep it in my locker till like the next lab period. All the methylene chloride would have evaporated, then I can wash the sodium sulfate down the sink drain. It's just sodium sulfate and water. Okay. So here's our organic layer. It's going to be evaporating from our beaker. If I want to speed it up, I can have this inside of a warm water bath. Let me set one of those. Turn on my water to warm it up. I need to look for a giant beaker that will hold this big beaker. I'm rating all the lockers that you might have been in. Big enough? I don't think this one's the same size. Yeah, they're both 800. Actually, I think I gotta go into the other stock room to grab one, so I'll be right back. Okay, let's see if this one's a good size. Yeah, I think that's gonna work pretty good. Get some warm water in there. There we go, that's looking pretty good. And then I will put that in the fume hood as well. That'll speed things up. I'll walk that over. And while I'm letting that dry or evaporate, I can work on my aqueous layer. And also, I want to fill in my extraction diagram because I haven't written everything in that we've done so far. Let's catch up on that. So what did we do here? I had the dibromobenzene, the neutral compound, in the presence of methylene chloride, trace water. So I did 2 dries of the water. What was the first thing I did to dry the water?
You added the brine solution.
Yeah, about 20 milliliters of brine, pre-dry. And then in my aqueous layer, what did I get?
You get mostly water,
Huh? What else?
sodium, and chloride.
Is this solution, do you think, is it saturated?
I'm unsure.
It was saturated when it was brine, but now it's drawn some trace water out of the organic. So I'd say maybe it's not saturated anymore. It's been diluted a little bit. Okay, I got that. And then the methylene chloride, the neutral compound. Oops, it's ugly. And then the very trace water, just a little bit of water left. What do we do with that? How did we do our final dry?
We decanted.
Yep. No, what do we add before the decant on that?
What is it? It's the hydrogen sulfate or hydrogen sulfide?
Sodium sulfate.
Sodium sulfate. There we go.
Na2SO4. And we made a sodium sulfate hydrate. Hexahydrate is what you mostly make. And then this guy we're letting evaporate. And what's in the evaporation? What's the gas over here?
Methylene chloride.
Yeah, methylene chloride gas. And then we're left with a solid. That's the neutral compound plus the dibromobenzene. And the neutral compound, it's about 0.1 grams, and this is about 0.4 grams, so there's more of that. So we'll be able to do a crystallization on that once it all evaporates. But now let's go back to our aqueous layer. We have this aqueous precipitate. What should we do with this aqueous precipitate? It's got inside of it, it has mostly water, some kind of carboxylic acid. That's a precipitate. And what else? Sodium. What else? All right.
Hydronium.
Hydronium, good. Okay, so I want to get this acid all by itself. I want to get it away from the water, the sodium, chloride, the hydronium. What can I do to do that? I can do 2 things, actually.
Could you add the sodium sulfate?
No, sodium sulfate's for very trace amounts of water in an organic. This here is like all kinds, it's like 55 molar water. So sodium sulfate, it'll just dissolve until it's saturated. You know, it's not.
Could you filter it?
Filter it, we can filter it. Yeah, we can do 2 things. We can filter it off, filter off the precipitate, filter it, or extract with methylene chloride. Well, which one do you think I'm going to choose to do?
If the crystals are too small, don't you want to do the extraction?
Yeah, that's right. What do you think of these ones? How do they look to you?
I don't know.
Hard question. You haven't had a lot of experience with
Yeah, I just sort of see a white mass in the.
Yeah. It actually, I know from experience, it'll filter pretty good. So we're good to go. I'm gonna filter it. So we're gonna do a vacuum filtration. You remember those? Or those of you, crystallization lab? I don't think I haven't had a lot of those turned in yet. But I showed a vacuum filtration during the crystallization lab. And now I'll show you that. So we have our precipitated carboxylic acid in here, and we want to separate it out from the water, sodium chloride, hydronium. So we're going to do a filtration. So we'll do a vacuum filtration. Let's set that up just like we did last time. I have a water trap bottle here that is already attached to a ring stand, so that makes it convenient. And when I'm looking inside of here, the longer glass tube will get hooked up to our water aspirator. I'm gonna push it on there, then I'm gonna I'll bring the laptop over for you guys to see it. Just a second here. So here we are. I just hooked it up to the water aspirator. Yeah, so there's a side arm right here. And the water aspirator has the bottom of it has a splash guard. Can you guys see this blue splash guard right here?
Yep.
Thanks. All right, and then now I will hook up my filter flask. It's very important to not get rushed at this point and use a filter flask that's dirty. I see this a lot. Students will have like the last experiment's mother liquor, and they'll just hook up the new experiment. And then when they filter the new experiment, the filter paper doesn't work, and the sample gets by the filter paper, and now it's in a dirty flask with all kinds of impurities. So it's not really easy to recover, not really recoverable. But if you have a perfectly clean filter flask like I do here, if something gets by the filter paper, it's fine. It's in a clean flask. We can recover it. Okay, so let me move this over to. This is going to be a good view for us. That's looking pretty good. So this filter flask, I'm going to hook it to this hose here, but I don't want to do it until I've got it clamped because these things fall over so easily. Okay, I got a good grip on it. It's not going anywhere. All right, and then I've got my Buchner funnel here. It's got two pieces. It's got the filter, the bottom part of it, one hole stopper. I'm gonna push this in here. I should get a good vacuum when I turn on my water aspirator to full blast. I checked each component, the water trap bottle, the hose, all the way through when I did the vacuum filtration during the crystallization lab last time. And that, if you haven't watched the video, you'll see that. So since I've already checked it once recently, I don't have to be as careful at first to check for vacuum. I'm just gonna set it all up like I did and check the vacuum at the end. So I'm gonna turn the water aspirator. It's gonna be kind of noisy, so you won't hear me. I'm gonna turn the water aspirator on full blast to get good suction. And I'll pull my palm over this and I'll see if I can feel it like suck. So let's check. Okay, water's on full blast. Oh yeah, I feel it, it's good suction. Did you hear that little? And then when I want to turn off the water, I've released the vacuum completely. Turn it off. Do you guys want me to check the vacuum again, though this time the fun way with the parafilm?
Yeah. I liked it.
You saw it in slow-mo, now you get to see it in real live speed. So I'm going to cut off some parafilm. Parafilm's like a laboratory Glad press and seal or saran wrap. It's a hydrocarbon polymer, and it's got this paper backing. You kind of just got to tear it a little bit, and then you can peel off the paper. And it's nice because it's real stretchy, but for organic solvents, it's not the best because it's hydrocarbon. It's very nonpolar. So if I had, say, some diethyl ether in here, and I wanted to seal off the top, parafilm's terrible for that because the fumes of the diethyl ether will dissolve the parafilm, and then it'll just, the bits of parafilm will fall and contaminate your organic solvent. So if you want to put parafilm over a solution, you only want to do it for aqueous solutions because Aqueous solutions won't dissolve the nonpolar parafilm, but yeah, organic. So you don't want to put parafilm over an organic solution. So I folded it in quarters, and then I'm going to twist, kind of pull it, stretch it over this, and it gets a good seal. So now when I turn the vacuum on, it's going to suck this parafilm down in, and it'll implode. I'll try to get close for you guys. There we go. 3, 2, 1. It's pretty good, huh?
That happened a lot faster than I was expecting.
Yeah, because the last time I did it on a slow-mo. Huh?
Yeah, it was the slow-mo.
Okay, you want me to do it? I'll do it again since I got a little more here. You can expect it to be faster. Okay, here we go. Fun, huh?
So is there a parafilm equivalent that you can use for organic solvents in the lab?
Usually what you'll do is you'll take a cork, like a tree cork, or a rubber stopper that's real resistant to chemicals, but I think cork's the best. Normally you would use a cork, and that doesn't dissolve in the organic thing.
Gotcha.
So if I wanted to say this was a solution I wanted to cover up, I'd grab like this kind of cork. And then I'd first check it on see how it's got the big end and the small end of the cork? I would check the big end of the cork, make sure it won't fall in there. And then I go with the small end, yep, and I can cork it that way. If you don't check the big end first, sometimes it's too small, it falls in there, and then it's like a puzzle to get it out. All right, so I got this here. Oh, what's that?
Just interesting, a little puzzle to try and get a giant piece of tree bark out.
It drops right in, no problem. But then when you're trying to pull it out, it's like, you have to get it out just the right angle. You're using usually a micro spatula. You got to like fish it out.
Yeah.
Okay. Next, I want to make the filter paper fit this Buchner funnel because I don't have the right size of Buchner funnel paper. So it's okay though. I'll just put this on here, and I'll trace out a circle and cut it. And I'm using pencil to trace a circle. Why do you think that is? Not pen.
For the same reason that the Sharpie gets washed off of the
organics so easily, huh? Yep, you got it. So even though this is an aqueous solution, it's still, I like to have it. Graphite is good for this organic lab. So I'll cut out my circle. I try to cut it a little inside of the pencil line, but it's not a big deal. I have a little bit of pencil line there. There we go. And then I'll put it in my filter. Let's see, can you guys see it? No, you can't. So I just like to push it in and try to make sure I got all the holes covered. Yeah, and some of it goes up on the side, which is fine by me. I'll show you when I'm done. So something like that. Okay, we're ready to go. I'm gonna filter this precipitate, and I'm gonna use water to filter it. I could cool the water down, and I could cool this too if I wanted to try to get a slightly better yield. But the benzoic acid and the orthotoluic acid, they're not very soluble in water, so I don't think I have to worry about it in this case. I'm just going to use room temperature water, room temperature solution. And so what I'll do is I'll turn my water aspirator on full blast again. And prior to adding this, I'm going to squirt some water on the filter paper because that'll help it suck down the filter paper, and it'll have less of a chance for crystals to get around the filter paper. So I put some water through here. You can see it sucking through. And then I'm going to take my precipitated solution. I'm going to swirl it, and then kind of dump it right in the middle. And then I can start rinsing it. And I'll put some water in here, and I'm going to be watching to see, is this solid that's in here, is it dissolving really well in the water, or is it okay? Nah, it looks fine, huh? So I'm not too worried about adding too much wash solvent right now, wash water. Let's get some more. Something's really stuck, huh? I think I'll use a spatula, kind of scratch it up. And as I said in the crystallization lab, filtrations, and this is not a really a crystallization, it's more of a precipitation, but they're never 100% yield, which is okay. If you really wanted to get it all out of here, after I did this, I could say rinse this with methylene chloride, put it in a beaker and evaporate it, and then like, I don't know, try to crystallize it to purify it or something. I think that's enough though. I got a little residual left, but less than a milligram probably. So I'll let this suck for just a little while. It is using tap water, so I don't like to waste too much water. But it doesn't take too long to get the bulk of the water through. And then I'll remove this and let it air dry. And it'll take a little while because water has a high boiling point. So I'll be patient with this one. I'll put it on a watch glass, the filter paper, and just let it sit. I'll probably come back to, not tomorrow. Maybe I'll come back tomorrow. No, I don't think I'll come back. No, yeah, maybe tomorrow will be good. Maybe I'll come back tomorrow, do some more with this, and see what we got. So I think that's enough time of suction. So should I just turn the water off now while it's under vacuum?
No, you got to break the vacuum like that.
Break the vacuum. Yep. I gotta,
Sign in the lab says.
yeah, break the vacuum. Now I've broken the vacuum. There's air is freely coming through. I can turn off the water.
What happens if you don't break it?
Yeah, if I kept this on and then I turn off the aspirator, it's no longer sucking air this way. And there's a good vacuum setup inside of this filter flask, inside of the water trap bottle. So since there's a vacuum here and no longer pull there, tap water can get pulled through our tube, can start to fill up our water trap bottle, and then we can start to get tap water into here. And I don't want tap water in there because what if I wanted to get a second crop or something? So this water trap water is actually, it's like a fuse. It's helping me. It's got to fill all this way with tap water before it starts to fill this up. But if I'm breaking the vacuum, then I don't even have to have this dealt with. Another reason why we do this is sometimes, for whatever reason, the aspirators get old or your splash guard is pushed up too much. It can cause backflow. So like, let's say I have this set up to go into to suck, and I'm like, oh, I'm gonna go wash a couple dishes and let this suck for a couple minutes. During that couple minutes, sometimes you can have backflow coming, and it'll start filling up, and then it'll start filling up. So it's a good safety thing, keep your product safe. Okay, so now this, to help this dry a little faster, I'm gonna grab a watch glass, put it on there. I don't have to weigh this watch glass because this won't be the one that, I'm not to the point where I'm weighing yet. And I need some tweezers. I have some over here. And I'm just gonna carefully take this filter paper out like so. And now it'll dry faster than when it was inside of this. And oh, I should have labeled this too. I'll label it underneath here. This is my acid, huh? 21, got it. Okay, so I'll let that dry on its own, and let's go check out our evaporating organic layer. Still nested, and it's still got quite a bit. This was a larger scale evaporation. I think what I'm going to do is, this is a good pausing point. I'll just leave this in a fume hood, and I'll come back tomorrow. It'll all have evaporated by then, and this will have air dried by then. And I could scrape this off onto a pre-weighed watch glass to get the mass of the recovered acid. And this will have evaporated, so I can weigh the beaker and get the mass of the organic neutral and benzoic acid. Actually, this is the impure neutral compound because it has the dibromobenzene. And then I'm going to take this solid, impure solid, do a crystallization, get that by itself pure, get its mass again, and then I'm going to take an iron and NMR, and we'll figure out what they are. All right, now it's just time to clean up. Actually, I'll show you a little bit of that. Let me put this away first. Okay, so one thing I want to show you is our acidic layers. I got this layer that was a 6 molar HCl. It was a sodium hydroxide extraction that then we made acidic with 6 molar HCl. Got those two. Let me make sure. Yeah, plus 6 molar HCl. 1 molar HCl? No, this one I think is basic. First, yeah, I didn't write it down. We added 6 molar NaOH to this one. So how am I going to quench these? I should have, I got 2. No, I only had to do this one once, huh? Because I got no precipitation the second time. But this here is acidic, huh? That's right. This is my second acidic layer because I filtered out the carboxylic acid. So I've got 2 acidic solutions I want to deal with. I don't want to put them right in the waste bottle as is. I want to quench them first. How do I quench them?
Use sodium bicarbonate, right?
Yes, sodium bicarbonate.
We use sodium bicarbonate to quench both acidic and basic solutions, and sodium bicarbonate is just baking soda you probably use with your making cookies or cakes and bread and things. So bicarbonate quenching an acidic solution, we use it that way because we'll have excess hydronium, and what will happen is the bicarb, this is sodium bicarb, or hydrogen carbonate's another term because it's got 1 hydrogen. It can deprotonate the hydronium, and when it does, it makes water, not basic, and carbonic acid, which is a little bit acidic, but it's actually very unstable. It decomposes to, in this mechanism, this is what I believe the mechanism is, because it's so quick, I'm thinking it's got to be unimolecular. And what it'll do is it'll create more water, not acidic, and carbon dioxide, which bubbles away, and that's what we see when we add the acid to the acidic. When we add the bicarb to the acidic solution, we see the bubbles form. This is also what you see when you say dissolve an Alka-Seltzer tablet or an airborne tablet. A lot of things you dissolve them in water, the solids, and the solids have bicarbonate, not hydronium necessarily, but like a citric acid, something like that, that will cause this carbon dioxide reaction to occur. And when you're done, you have a lot less hydronium in your solution, so your pH goes closer to 7. So you've neutralized it, quenched it.
And should I put the sodium bicarbonate in like a small Erlenmeyer flask and add the acidic solution?
No.
If you
No,
want it
why
to
not?
shoot out the top, then yes.
Yeah, it can volcano out, huh? So instead, get a big beaker. And then just grab a little sodium bicarb. Pour that in. With experience, you know how much to add. And I can add a little more too. And now the first one is this one. Yeah, this is a 6 molar HCl. So let's see what happens. Nice, huh? Can you see it bubbling? So the sodium bicarbonate is getting protonated and it's becoming carbonic acid, which is unstable, and it decomposes to carbon dioxide gas, bubbles, and water. So we're seeing that carbon dioxide. Yeah, so, and I can give this a rinse if I want to get a little more out. And this, do you think I've quenched it? Does it look like it's no longer acidic over here?
Since
Any
you still have
evidence?
excess bicarbonate.
Yeah, I've got excess bicarb. It looks like it's quenched. Now I'll do the second one too. This is the second acidic layer from the filtration. This one's a little less acidic. It fizzed a little bit.
So is it better to add the solutions to the solid
Yes.
like you're doing now? Okay.
Yes. In general, you always want to add the stronger thing to the weaker thing. So these acidic solutions are more acidic than the bicarb is acidic or basic. It's pretty, the bicarb's mild.
Gotcha.
If I add the sodium bicarb to, like, say, for example, if I would have added it to this sodium bicarb to the acidic solution here, it could volcano out as well.
Mhm.
And it's more violent. Like, have you heard of the idea, like the concept of do what you oughta, add acid to water? Or do what you oughta, add acid to water?
I don't
They're saying,
think I've heard that before.
what they're saying is add the strong concentrated acid to water to dilute it. Don't add the water to the strong concentrated acid.
Gotcha. I do remember hearing
Because,
something.
yeah, so if you add the strong concentrated acid to water slowly, it's going to heat up and react, but it's going to be cooled by that water, the weaker water, and it's going to absorb all that heat. Whereas if I have, say, concentrated sulfuric acid here, and I add some water to it, it's in sulfuric acid mostly, and that's not good at containing the exothermic heat, and it could splash out concentrated sulfuric acid on me.
Gotcha. Okay.
I'd rather add the concentrated sulfuric acid to water, and if it gets too violent, it's splashing out mostly water on me.
Yeah. Which you still don't want, but yeah.
You don't want that either.
Yeah.
And then, so this guy is pretty good here. I could add this, I think since it's neutral, I can add the hydroxide to this now too. And with this one, it's not as pretty as or not as interesting as you don't get the bubbles, right? Because what's gonna happen now is the sodium bicarb, the bicarb, it's an acid as well as a base. So it's gonna get deprotonated by the hydroxide to become carbonate.
Basic solutions. So when you have a basic solution, you have excess hydroxide, the strong base, and I have the pKb for it here. That's not the pKa, it's pKb. And like pKa's though, the lower a pKb, the stronger the base. So this is pretty strong, it's almost 0. So this is going to react with our bicarbonate, but in this case, the bicarbonate is going to act as an acid, not a base. And it does both. It's basic on this end with the O-, and it's acidic on this end. So the hydroxide will deprotonate that and create carbonate. And carbonate, it's a pKb of 3.7. It's a weaker base than hydroxide. The higher the pKb, the weaker the base, just like the higher the pKa, the weaker the acid. And then we don't produce carbon dioxide, so we get no carbon dioxide gas, so no bubbles in this quenching, not like the acidic one. The carbonate is a much weaker base than hydroxide. It might not appear like it, 3.7 pKb to 0.2, they're pretty close, but pKb is on a log scale. Remember, pKb means negative log of the kb. And so it goes by powers of 10. So if I take the pKb of carbonate and subtract the pKb of hydroxide, I see the difference in pKb is 3.5, and that's actually means that the carbonate is 10 to the 3.5 times less basic than hydroxide because it's power of 10 log scale. And so this is over 1,000 times weaker base than hydroxide. So we have made the solution less basic and quenched it.
And that's not gonna bubble or anything. So I've got the carbonate there. And then this was my other aqueous layer. So remember what this layer was? This was the last aqueous layer. We added, no, this is the organic layer, huh? Never mind, this is the organic layer. So this doesn't need to be quenched. The organic layer doesn't really get acidic or basic. This will go straight into the waste container. I'll go pour that now. Oh, and I just did something that sometimes I don't do. Depends on your style. So I just got rid of that organic layer because I felt very confident it had nothing I wanted in it, but I might have been wrong. So I know I got this carboxylic acid. I see the precipitate, it's a lot of precipitate, I'm happy. But the organic layer that's evaporating in the fume hood, I haven't really seen that solid yet. So I was a little bit quick to get rid of this organic layer, but I think I'm all right. I had a friend of mine in grad school, Cobalt, he never wanted to throw away any of his aqueous layers and organic layers just in case there was something in it. So we would have a big long bench like this, and we'd put like a piece of tape down the middle and say, okay, Cobalt, this is your side, this is my side. And he's like, cool. And then throughout the week, he would have beakers and Erlenmeyers and things covering every surface of his bench. So he'd have about like 150 Erlenmeyers and beakers all over. He would have no more room to set anything down. And then I'd be like, Cobalt, what are you doing? He goes, oh, I'm not a chucker. I'm not going to chuck this away because it might have something I want. I might, after I take the NMR, I might realize that, oh, I want to check that other layer. And then he goes, yeah, you can't be a chucker. I go, I know, but you have no more bench space. And I'm like, do you even know where things are? And I'd ask him like, okay, last Wednesday, where's the aqueous layer from that reaction you did in the morning? And he'd be like, boom, this one. And he'd pull it up and he'd be right. I was like, God. But then he would want more bench space. So we'd have a piece of tape across the bench, and he'd go, hey, Mark, can I get 2 inches? Just 2 inches. And I'm like, okay, cool. So we lift up the tape, we move it over 2 inches, and then within like half a day, it's filled up with the beakers and Erlenmeyers.
Oh my.
And I was like, Cobalt, you gotta wash some of your dishes. Like, if it's a week old, you're not gonna want it. He eventually would. He would do like a pull an all-nighter and clean up everything. It's funny. Cobalt's a great chemist too. This is his glassware.
He was quite the thorough individual.
Yeah, yeah, super smart. He helped me out a lot. He was like a couple years ahead of me. I was lucky, except for the day he brought the durian fruit into lab. Oh my goodness,
Oh, that was that guy.
it smells so nasty. Okay, so I quenched the acids and bases, and the base. When you quench a base, it's not as obvious to tell. I do have sodium bicarb still in there, so I feel like I did a good job. But with bases, sometimes I'm extra careful and I say, you know what? I want to make sure I quenched it. So I'll just do a little pH paper. Easy enough, right? Doesn't take long. And I'm being good about using tiny bits of pH paper, right? So I'm not wasting too much. Big spatula here. Swirl it around. It won't be, yeah. Oh yeah, it looks good. It's green. So green, what pH is that? We're at like pH 8. And that actually makes sense. A solution of sodium bicarb is about pH 8. So that's what we want. So now I can put this in the waste container. Yeah, we're doing pretty good here. Just gonna wait till tomorrow.
Yeah. And the waste container, that's just sort of,
I'll show you, it's over here.
you just kind of throw everything that can't go down the sink into it, right?
Yeah, yeah. You know, it's changed over the years. We used to have we'd have an aqueous waste container, an organic halogenated waste container, and then an organic non-halogenated waste container, like molecules with halogens or not. We'd segregate it into 3, and then solid waste. But now they've just decided people aren't good at sorting them anyways, so they just have us put the aqueous and the organic. Both the aqueous and the organic in here, and then the company that takes it away for us and properly disposes of it, they separate it out. And it's actually pretty expensive. Sometimes some chemicals, it costs more to get rid of them than to buy them initially.
Really?
So you want to try to avoid making too much waste, you know? And so, sometimes when you're buying chemicals, it could be cheaper to buy like a 500 gram bottle over a 100 gram bottle. They're like a lot cheaper per gram. So you're like, oh, should I get the 500 gram bottle instead of the 100 gram bottle? And you're like, but I don't even need 100 grams. So, and I'm going to have to eventually get rid of it. So I'll have to pay to get rid of it. So sometimes you got to think ahead and be like, oh no, I'm not going to do that. I'm not going to buy it much. That happens a lot in labs. Like when I was at Davis, there'd be a professor that retired, and his lab would be filled with chemicals from like the 1960s, 70s, 80s, 90s. He's got all these old chemicals, and they would like, anybody want them? They're like, please take them, because to pay to get them disposed is expensive.
Yeah.
But then the other labs have a bunch of chemicals too. Like, hey, our stockroom's full. Like, yeah, sorry, you're gonna have to pay to get rid of this.
Yeah.